Hello, here's some more questions on nuclear physics, particle physics, radioactivity. We'll see what they are. We start here with a nuclear reaction represented by this equation. Okay, it takes place in the core of a nuclear reactor at a power station. Describe how this reaction can lead to a chain reaction. Right, the important thing in a chain reaction is we need something that's come out on the right-hand side that can then be plugged back into the left-hand side. So we need a neutron in order to make this uranium nucleus unstable. So the neutron gets combined with the uranium, makes it unstable. That then splits, but is now produced 3 more neutrons. So we want to say that the neutrons released can then interact with other uranium nuclei, causing further fission reactions. So yeah, that's the key part. Explain the role of fuel rods, control rods, and a moderator. Okay, so fuel rods, that's where the where the fuel is. That's where the radioactive material is. So in this case, where the uranium is. So that's the radioactive material. The control rods, they are controlling the rate of reaction. The number of fission events that we're going to be getting, because they will absorb neutrons. If you push the control rods in, then they will absorb some of these neutrons that are causing the chain reaction. So absorbing neutrons. So you can put this into fuller sentences when you're writing it out. And the moderator is slowing the neutrons, because we want to have what they call thermal neutrons, slow moving neutrons. If they're moving too fast, you can't get them to be captured as easily by the uranium nuclei. So we want slow moving neutrons. So passing them through the moderator, which might be something like heavy water or something like that, or carbon, that will slow the neutrons down, so they're more likely to cause further fission events. C. In the nuclear reactor of a power station, each fission reaction produces 3.2 times 10 to the minus 11 joules of energy. The output power is 3 gigawatts. Unfortunately, not 1.21 gigawatts, but just 3 gigawatts. The efficiency of the system is 22%. Calculate total power. Right, they're walking us through some calculations here by the look of it. So the total power output, if we've got 3 gigawatts, is being output in electrical power. So that's 3 times 10 to the 9. But that's only 22% of the whole thing. So we're going to have to multiply by 100 over 22 in order to get the total produced by the reactor core. So tapping that into the calculator, 1.36 times 10 to the 10. So 1.4 times 10 to the 10 watts. So, or 14 gigawatts. What we got now? Let's done that one. The total energy output of the reactor core in one day. So they've given us the number of seconds in a day, so we just need to multiply those together. So energy per day is going to be our 1.36 times 10 to the 10 multiplied by 8.64 times 10 to the 4, which gives 1.18 times 10 to the 15, or 1.2 times 10 to the 15 joules. Okay, this is all easy enough so far. Mass of uranium-235 converted in one day. Right, so how much mass have we got in each day? We need to have how many reactions a day? Here's that number that we want there. So the reactions per day is going to be what we've just worked out here. It is 1.18 times 10 to the 15 divided by 3.2 times 10 to the 11. So that's the reactions per day. And then we're going to have to multiply that by, here we go, the mass. So multiply that by 3.9 times 10 to the minus 25, because this is the number of nuclei that are decaying, and that's the mass of each one. So that is going to give, that's also giving me more time to type all of this in, 14.4 kilograms. So let's say 14 kilograms, as we're stretching to go to 3 sig figs. Discuss the physical properties of nuclear waste that makes it dangerous. Right, well, it's highly radioactive. A lot of it has a long half-life. The problem with the radiation is it's ionizing, so it can damage cells and other, natural organic material of that sort of type. So yeah, if you mention the word, radioactive, ionizing, and what that does, and the long half-life, then you've got quite a lot you can say on that last bit. So there we go, that's question number 1. Let's try the next one. In experiments carried out to determine the nature of atoms, alpha particles are fired at thin metal foils. Right, we've done this before. Describe how the alpha particle scattering experiments provided evidence for the existence, charge, and size of the nucleus. So we've got 2 pairs of things that we want to mention in this. We want to say that most of the alpha particles went straight through, passed straight through. And we also add then also some, as in very few, so it's more like a few, deflect. So you don't want to say reflect, because they're not reflecting, they're deflecting. Deflect over large angle. So they're the 2 main observations. And then off of those, we want to say that is therefore, let's do a therefore on that one. Mostly empty space in an atom, and for the other one we've got therefore small positive nucleus, positive charge nucleus. So that's around about 10 to the minus 14 or 10 to the minus 15, something like that, whatever you want to put on there, in diameter, radius. It's all a little bit fuzzy around about there. So yeah, that's good. We've gone through that quite a few times. Describe the nature and range of the 3 forces acting on the protons and neutrons in the nucleus. Right, so that's 3 of our 4 fundamentals. So we're not including the weak in this, because the weak is mainly going on inside the protons and the neutrons. That's going between the quarks. So we've got gravity. So we have to describe nature and range. So that is infinite range. It is it's weak. It is attractive. For things with mass. So you need mass is the thing that is like the, what's the word I'm looking for? Mass is the property of the matter that you need in order for it to engage in the gravitational attraction. And yeah, that seems to cover these sort of things. Right, okay, so then we'll go with strong, which is short ranged. It is strong. It is attractive at around about 10 to the minus 14 or 10 to the minus 15 meters. It is repulsive at shorter distances, at less than say 10 to the minus 15 meters. a meter over on that one. So that's good, and this is to do with color charge, so we can put that in. And then we've got electromagnetic, which I haven't left enough space for, but that is infinite. It's a sort of intermediate, is much stronger than gravity, but it's around about 1,000 times weaker than the strong force, than strong. It is, what are we talking about? Protons and neutrons. So it repels protons. It doesn't affect neutrons. You've got a lot of things you can say here. And it is electric charge. So that is covering more than enough there to get your marks. Then in C, the radius of a uranium nucleus is that, the average mass of a nucleon is that. Estimate the average density. Right, so we're going to need the mass over volume. So we've got, what we've got, 235 nucleons multiplied by mass per nucleon. And our volume is going to be 4 over 3 pi r cubed. What they say r was 8.8 times 10 to the minus 15. That's quite a lot to, cube that, don't forget that. Quite a lot to type into the calculator, so this is going to take me a little while. 4 and then pi, 8.8, 10 to the minus 15 cube, so 1.40, I'll just leave that out, kilograms per meter cubed, because I can't really put the 0 in, we're only to 2 significant figures on the input data. Is that everything? Oh no, we have got one last bit. State one assumption made in your calculation. I mean, I suppose they're not perfect spheres, so we've assumed that they're perfect spheres. Otherwise, you've got a problem. You might, if they're a bit lumpy, you've got things that look a bit like a sphere but lumpy shaped or something. We're including this extra volume, this empty space in the spherical volume. So we're assuming that they are perfect spheres. Cool, so that's covered that one. I'm hoping I'm going to get all 5 of these questions into one video. So we'll see how we get on with the others. Third one, describe the process of induced nuclear fission. So the point of that is you fire a slow-moving neutron. That goes into, you fire that into a uranium nucleus, and that causes fission. The nucleus will divide. So it's that firing in this neutron in there, that's the induced part of it. Where the uranium was sitting there relatively happily until we fired that neutron in, and then that caused it, that induced it to divide. So explain how nuclear fission can provide energy is because the binding energy of the products is greater than the binding energy of the original material. And this difference in the binding energy, that is the released energy. So the products are more tightly bound than the initial material. They're more stable. So that extra energy is then released. Suggest a suitable material which can be used as a moderator in a fission reactor and explain its role. Right, so the moderator is about slowing down the neutrons, because a fission event, so fission will produce neutrons, but these are fast neutrons. We want to slow them down because slow neutrons have got more chance of causing further fission events. So you pass them through the moderator, which might be something like heavy water, say. Water made with deuterium as its hydrogen. So we have that, and then that leads to slow neutrons, and then they can then go on to more fission. So we're back to the start. So yep, that was all fairly straightforward. Question 4. A sample of radioactive isotope contains 4.5 times 10 to the 23 active undecayed nuclei. Half-life is 12 hours. Calculate the initial activity. So the activity is the decay constant multiplied by the number of nuclei. The decay constant is log 2 over the half-life. So we've got n log 2 divided by the half-life. That is equal to what we got, 4.5 times 10 to the 23 multiplied by log 2 divided by 12, but that's hours, so you need to multiply by minutes and then seconds. So let's put all of this into the calculator, and that is giving 7.22, but let's go with 7.2 times 10 to the 18, so becquerel or seconds to the -1. The number of active nuclei of the isotope remaining after 36 hours, so that is 3 half-lives. So after 3 half-lives, we'll be down to half, a quarter, an eighth. So that is an eighth of what we originally had, which is an eighth of that 4.5 times 10 to the 23. So 5.6 times 10 to the 22. Then the number of active nuclei of the isotope remaining after 50 hours. Right, so after 50 hours, so this is where we've got our, if we go to our n equals n0 e to the minus lambda t, that's our decay equation for a radioactive source. Now remember, with lambda, we already know that, lambda t is lambda we know is log 2 over the half-life, and then we multiply that by t. So that's what we've got in here. So we can easily change the exponent here and say, right, well, that's n, what was n0? 4.5 times 10 to the 23. And then we're going to have e to the minus log 2 times t over the half-life. And as long as we stick in the same units of time, we're fine. So we can just do 50 over 12. We don't have to change things into seconds. You can just leave it in hours. So yeah, work that out and we'll have what n is. So let's type all of this in. 1.5, I'll leave the 10 to the 23 off and just put that in at the end. And we got 2.5056, blah, 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 blah. So 2.5 times 10 to the 22. That gives us that one. So that's done all of A. B, explain why the activity of a radioactive material is a major factor when considering the safety precautions in the disposal of nuclear waste. Right, well, you've got a sort of spectrum going on here of if we're going high to low on our activity front. If you've got high activity, as in we've got a high value of our decay constant, then you've got, essentially you've got big initial problems. You've got a short-term high radiation. So you've got a lot coming out in the short term that you need to manage in a certain way. If you've got, so that's for a high decay constant. If you've got a low decay constant or low activity, then you've got low level but long-term radiation. So you need to be able to deal with the consequences over centuries for what this low-level ionizing radiation is going to be doing. So you need to be able to cope with both types of product when you're dealing with radioactive material. Have you got a really highly damaging short sudden burst because you've got high activity, or have you got a lower level but still continually damaging over a long period of time? So they're the two options that you've got where the activity comes into it. Right, on to the last one. There are two types of beta decay, beta plus and beta minus. An isotope of carbon decays by beta emission into nitrogen. isotope of phosphorus decays by beta emission into silicon. Right, so complete these decay equations. Well, they've given us some numbers already here. So this carbon is going from it's going to 15.7. They've already given us here in the question. So let's put that in, and let's put the silicon in on the one below. So 30 and 14. So we've got those in. Now we need to make the numbers add up. So, well, we know the electrons are always going to have 0 on top anyway, but this is going to tell us which one is actually the electron and which one is the positron, because we need the numbers to add up at the bottom, left and right. And then that is going to tell us which neutrinos we're putting in. So if you've got an electron, you need the anti-electron neutrino. And if you've got a positron, you just need the electron neutrino. So let's fill those in. State the two beta decays in terms of a quark model of the nucleus. Okay, right. So for beta minus, that means we're getting a neutron to a proton. So we're going from beta plus is the top one. So beta minus, for beta minus, we're going from a neutron to a proton. So we're going from up, down, down in the neutron to up, up, down in the proton. And beta plus is the other way around. So we're going from proton to neutron. And we can see that in, if you look at the beta plus one down the bottom here, see the proton number here has dropped. We've now only got 14. So one of those has gone up to, it's still in the nucleon number, but it's not one of the protons, it's one of the neutrons. Name the force responsible for beta decay. That is the weak interaction, the weak force. So yeah, it was 5 fairly quick questions. We've seen a lot of that stuff before, but it's always the case when we're going through these. But the repetition, I don't always say it, but the repetition is so useful.